Hello everyone and welcome back. I'm Mahnur and today we will be continuing on with the chapter of kinematics, specifically for AS level physics. Now, last time we had first introduced the concept of kinematics as the study of motion in itself, right? We had introduced it as the study of motion. And in relation to this, we had defined some very fundamental concepts that we would encounter time and time again in this entire chapter. And those are as follows. We had defined distance as the length of the path covered by a moving object. We defined displacement as the shortest path between 2 points. We defined speed as the rate of change of distance, velocity as the rate of change of displacement, and then finally acceleration as the rate of change of velocity. Now, these fundamental quantities, if you recall, we had understood as the ABCs of this chapter, meaning once we know these, we know how we can study motion to begin with. But then comes a very simple question that we didn't really raise last time. How do you even study motion to begin with? Do you just hold up a magnifying glass in front of some moving car and then see what kind of an answer you get? Well, it's not that straightforward. Here we have to first establish what kind of approach do you want to take to begin with. In which case there are basically two approaches that you can take. You can take a quantitative approach or a qualitative approach. Now, a quantitative approach means you're quote-unquote quantifying something. And if you're quantifying something, that means you expect a numerical answer at the end. So you can think of it as a numerical approach, in which case you're most of the times relying on equations. On the other hand, a qualitative approach is where you basically do anything but rely on numbers, in which case you expect yourself to be able to describe different types of motion without needing to rely on some equation, in which case it's more so a conceptual understanding of how you can describe different types of motion. And that's mostly done through a diagrammatic kind of analysis. And that kind of a diagram could even mean a graphical approach. And that's usually what you do in kinematics. So in our case, it's going to be predominantly a graphical approach, because of which we'll be relying most importantly on graphs. Now, for this, we need to first understand a basic notion of what a graphical approach entails. And in regards to kinematics, there are going to be two types of graphs that we will study. There's going to be displacement versus time graphs, and there are going to be velocity versus time graphs. So let's look at each of these one by one and understand some of their important features that will help us better understand different types of motion. Let's start things off with the simplest one, that is displacement versus time graphs. Now, could you guess what kind of a graph this would be? Well, if you have already covered O-level physics, you might already then remember that a graph that is displacement versus time basically means you have time on the x-axis, represented with t, and displacement on the y-axis, represented with s. Now, if you wanted to just guess what feature we could look at for a particular graph, any kind of graph really, your first guess would be the quote-unquote gradient of the graph. Suppose our graph shape, for one reason or another, is currently this kind of a shape. We don't really need to worry too much about why we're considering this shape. We just want to see some important features first and foremost. Now, when it comes to measuring the quote-unquote gradient of this graph, that's basically a measure of the slope of the graph. Slope meaning how steep this graph is. So when you are trying to measure the gradient or slope of this graph, you're basically comparing how the quantity on the y-axis is changing with respect to the quantity on the x-axis. In our case, those x and y-axis quantities are nothing but time and displacement respectively. So I can basically take this expression I've already written and rewrite it as replacing delta y with delta s and delta x with delta t. Now look at this expression carefully. Notice how it's a change in displacement divided by a change in time, or the time covered, or the time duration. This is nothing but an expression of velocity. So this is remarkable. We have established one very important feature of a display of all displacement versus time graphs. That is that the gradient of a display, or the slope of a displacement versus time graph, represents its velocity. And so you can take any two graph shapes, so for example this purple one compared with, let's say, this red one, and then you can compare their velocities just by comparing their slopes. And here we can even do that without needing to rely on a numerical number. Take the purple graph for instance, and let me label it 1, and I label the red graph 2. Notice how the first graph is the first graph line is a lot more steep than the second graph line. In other words, the first graph line, that's purple, has a larger slope than the second graph line colored red. This goes to show that if we had, let's say, these two moving objects, let's say the first one is a purple car, the second one is a red car, the purple car is a lot faster than the red car, right? The gradient, since the slope of the first graph is a lot larger than the second graph, which is to say, so notice here how you were able to compare their velocities without even needing to evaluate a number. You were able to conclude that the gradient of the first graph line is larger than the gradient of the second graph line, which is to say that the purple graph line is steeper or has a larger slope than the red graph line, which is to say that the purple car, let's suppose, is faster than the red car. So see how we basically conducted a qualitative analysis of two moving objects, a purple car and a red car, without ever worrying about a number. So here we can immediately see how beneficial this approach is. Now let's see what important features do we have for a velocity versus time graph. Velocity versus time graph. Here it's easy to guess what kind of a graph this would be. Here you would have time on the x-axis, as usual, represented with t, and then on the x-axis you would have v, velocity. Now let's see over here, what does the gradient represent? Once again, I'll take an arbitrary shape, let's say this one. Here too, I wish to measure the slope of this graph by measuring its gradient, which would once again be seeing how the quantity on the y-axis changes with respect to the x-axis. This time the quantity on the y-axis that I have is velocity, and on the x-axis once again I have time. Now I have a measure of the change in velocity for each interval of time. That is nothing but acceleration. So remarkably, for a velocity time graph, we realize that the gradient actually represents acceleration. Once again, we've reached a remarkable conclusion. And now here too, we could have yet another purple and red car and compare their slopes and see which one has a larger acceleration than the other, simply by comparing their velocities. I want you to now pause this video and take your own guess. Is the purple car labeled 1 having a larger acceleration than the red car, or the other way around? And notice how you took this approach. So I want you to try that one yourself. Now it turns out that when it comes to a velocity versus time graph, there's one more feature we can look at. That is the area underneath the graph. But instead of me just directly telling you what that area under the graph means, let's actually figure that for ourselves. So let me draw one other graph over here. Velocity on the y-axis, time on the x-axis. This time let's suppose the shape I take is a bit more simple. Let's take a horizontal line. What this means is that with passing time, or with the passage of time, the value of velocity, whatever that velocity is, suppose it's just some arbitrary value v, it doesn't seem to change with time. So that's basically one way of seeing what constant velocity looks like, but more on that later. Let's focus more so on the shape of this graph, and instead of calculating its gradient, let's suppose we are interested in figuring out what the area underneath this graph is. For this, let's suppose I'll mark off a region like this, and it's this shaded region that I'm interested in evaluating the area of, right? Now on the x-axis, I'll have some time interval that has passed from 0 up to some time t, right? Now if I look at the shape of this shaded region, it's basically the shape of a rectangle, which means the area underneath the graph in this scenario is basically the area of the rectangle, which we are all familiar with, is just length times breadth. Here, the length itself, as you see here highlighted yellow, is nothing but a time interval from 0 up to some arbitrary time t, which would just be t minus 0 t. Let's call that the length. Whereas for the breadth, we have this gap, which is v minus 0 equals v. And so I write v over here. Now this seems quite straightforward, sure, but notice how velocity multiplied by a time interval is nothing but a rearranged definition of velocity. And I'll just quickly write it over here just for our memory, that if you recall, the definition of velocity was the rate of change of displacement over some time interval t. Notice how if I were to rearrange this, I get an expression for displacement. So v times t is actually just a measure of displacement. So remarkably, we found yet another feature for a velocity versus time graph, that is its area underneath that specific graph. In short, what we realize over here is that the area underneath the graph on a velocity time graph only is equal to the displacement covered by the moving object. So where a displacement time graph only really gave us valuable information from its gradient, the velocity versus time graph gives us important information from its gradient as well as its area underneath that graph line. And it must be noted, although here I had expressed this kind of understanding through just one kind of a shape, it must be understood that this works for any shape. Now you might be wondering at this stage, how on earth could I get the same expression v times t for any shape? What if I had a graph line like this, for instance? Suppose if I had this. Now here clearly the area underneath the graph is not really a rectangle anymore, it's actually a triangle. In that case, if I do evaluate the area, it would be half times base times height. The base would once again be some time interval t. The height would once again be some value starting from 0 up to some arbitrary value of velocity v. So clearly this time we have this extra factor of half coming out of nowhere. So how do we account for this in an expression for displacement? Here the factors don't really matter as much as the units do. If I were to conduct a unit based analysis of this expression, I get the following. Now the factor of half is basically unitless, so I could just replace it with 1. For velocity, I know the SI units are meters per second, so ms per second. And then for time, I know it's second. Second and second inverse cancel out and you're left with units of meters, which is basically the unit of displacement. So it's completely valid for us to claim that the area underneath the graph for a velocity time graph specifically will always equal displacement regardless of the shape of the graph. Great. So what we've concluded up to this point is that when it comes to a graphical approach, we have displacement versus time and velocity versus time graphs. For displacement versus time graphs, the gradient represents velocity. For a velocity versus time graph, the gradient represents acceleration. Moreover, And another feature of a velocity time graph is that the area underneath its graph line represents displacement. Great. Now let's see how does this fare for a practice question. Alright, so let's attempt this practice question. Now here we have the graph shows velocity time plots for two vehicles x and y. The accelerations and distances traveled by the two vehicles can be estimated from these plots. So we have two graph lines here. Now here we have a few options and we have to pick which statement is correct. Now once again, give this video a pause and then try to attempt this on your own. Understand different features of a velocity versus time graph that we have learned up to this point. Give it a good shot and then later we'll attempt this one together. Are you done? Let's see whether your answer is correct to the one we attempt together. Now let's look at each option carefully one by one. Now the first option says the accelerations of x and y are the same at 2.5 seconds. Now apparently the 2.5 second mark is basically the point where the two graph lines intersect. But even if these two graph lines are sharing a point right here, these graph lines obviously have entirely different slopes. We can clearly see that graph x has a larger slope than graph y. And for a velocity time graph, we recall that the slope represents acceleration. Clearly, graphs x and y have entirely different slopes, even if they're intersecting at the same point at 2.5 seconds. So A can't be correct in any case. Let's look at the next option. The initial acceleration of y is greater than that of x. Once again, this is incorrect because we can see how the slope of y is actually lesser than the slope of x. Not only that, but they're constant in their own regard. So they're not changing with the passage of time, and moreover, graph y starts with a smaller value of the slope and keeps it that way. So once again, B is also incorrect. Now we're left with C and D. The distance traveled by x is greater than that traveled by y in the 5-second period. This is where we'll have to evaluate this through the area underneath the graph. Let's first do it for graph y and then we'll do it for graph x. Now for graph y, we'll shade this region that we see right here, and if you notice, it's nothing but the area of a trapezium. So I can evaluate that pretty directly. So let me in fact call it displacement. Let me use the symbol for displacement in fact. Displacement for y, which would be the area of a trapezium, which we know is half times the sum of parallel sides times height. Now the parallel sides that we see here are the 2 mark right here and then a mark right here. We can see what that is by just simply extrapolating it, and we find that it's exactly at the 3-second mark. So you have 2 plus 3. Times the height, which would be this, which is exactly equal to 5. So this equals half times 5 times 5, which is 12.5. Right? Now let's see what displacement do we get for x. So now I'll just erase this. Focus on the triangle that we have for x. This is quite straightforward. It's just half times base times height. Half times the base would be 5 seconds and the height, if you notice, just so happens to be 5 as well. And here too we get 12.5 meters. So if we notice, if we go back to option C, it says that the distance traveled by x is greater than that traveled by y. But in fact, they're actually the same. So C automatically is incorrect, and if we check D, the distances traveled by x and y in the 5-second period are the same. That is in fact the truth. So here the answer is D. Hope you got the right answer. Alright, so let's wrap it up here. Once again, go over these concepts once again, and then next time we will see how we can conduct a quantitative approach of analysis in kinematics. Thank you. Welcome back. I'm Mahnur, and today we will be continuing on with the chapter of kinematics.